Okay, any questions before we get started? Not about work energy, just are we still gonna, as far as I know, we're not making any major changes to how the course is run. So, you know, the whole one column for mid-unit quizzes, 2 columns for the end of unit exams. What else? The goal is to finish by end of April with all of our content, and then we'll do a mock exam, and then AP exams start like May 2nd, May 3rd, whatever that first Monday is. AP Physics 1 exam is not until May 12th, so that first week, though, are some big AP exams that we're expecting not to have everybody, and so we usually don't cover content when half the class is gone, right? And so the goal is finish by end of April with our content. And we have basically 3 big units and 3 little units, okay? And so it's gonna feel quick paced again, just like we had in the fall. So please don't get behind, okay? Okay, so let's talk about work. Let's do work. Now work is not a generic term like we use in everyday life. Work in physics means something. And so what does work mean? Well, come on, zoom in. Okay. So work in physics, by the way, has a variable W. Where have we seen that in the past? Weight might have a capital W. Officially, AP exam formula chart. The capital W means work. Yeah, 25. And so capital W is work. And in order to do work, you got to have F times D. Now, what's the capital F? A force. And what do you think is lowercase d? A distance. So you have to exert a force on an object, and it has to move a distance. So this is as simple as it gets. If you were to Google work equation, this is what would pop out. But wait, there's more. You'll know AP, right? There's always more to it. And so I'm going to add in some nitty-gritty details about this force and distance. They have to be parallel, okay? They have to be parallel to each other. And so what does that mean? Well, previously we did circular motion, right? And so previously, that's what we ended with in December. Circular motion, maybe it was a ball on a string, right? There was a force, tension force, pulling it, but what direction was it moving at that moment? It's being pulled vertically, but in that moment in time, it's moving in the horizontal maybe, right? Just for that split second. Look at a short amount of time, right? These are not parallel. Does the string do work on the ball? No, these are perpendicular, which means there's a direction change. Now that makes sense back with circular motion, right? Direction change. But for work to be done, we want to have a parallel, okay? And so we can take it as easy as pulling a box, okay? And so what if I pull a box to the right across a flat surface? It's going to move maybe sometime in the future. It's over here. And so it's moved a distance d. Is work done by the applied force on the object? Yeah, that force and that distance traveled are both horizontal. Now, is it right and right? Does that make a difference? Ooh, I don't know what that sound was. Well, let's compare. What if I've got a frictional force, but same situation, the box moves to the right? Is work done in that example? Yes. Are these the same kind of works? What's the story behind example 1? It moves to the right. It's pulled or pushed to the right, right? Someone tell me more about the motion of the box in the top example. The top example is slowing down? No, it's speeding up, right? You pull something at the same direction it's moving, that's going to be a speed up. What about the story of the second box? It's going to be slowing down because friction is pulling to the left, but it's moving to the right. Oops, not ring. Right. And so y'all remember forces. Y'all remember vectors, right? Correct? Okay. And so we've got a speed up in one, a slow down in the other, and I have different forces performing work on this object, right? Well, there is a difference. They are parallel, so work is being done. But to take it one step further, another version of your equation, by the way, both of these that I'm writing appear on your formula chart. If you have one nearby, you can find work equals a parallel force times distance, or you can write it as FD cosine theta. Now let's define what theta means. Well, Ms. Earhart, there's not a ramp here, so you don't have an angle. That's not how it's defined. Look at the formula chart. The theta, oh, never mind. It does just say angle, but I'm going to take it further. This is the angle that separates your force and distance. And so if you pull something to the right and it moves to the right, what angle separates right and right? 0. And so in the first example, this is 0 degrees. What's cosine 0 degrees? Not 0, 1. And more specifically, a positive 1. Compared to the second example, where friction's pulling to the left, but the box is moving to the right, what angle separates left and right? 180. So this one's 180 degrees of separation. What's cosine 180 degrees? -1. Okay. And so what we get here from this, both boxes examples, there is work being done. However, it's not identical work. First of all, you have different forces doing the pull, applied force, frictional force. So our subscript would be different, but you would also have a different sign. Now here's where it gets tricky, right? Work is actually a scalar quantity. So who remembers scalar versus vector? It doesn't care about direction, okay? And so your sign, I'm gonna write it a little differently to make it apply here. Your sign does not indicate direction. Indicate direction. So we do have positive and negative work, but it doesn't mean right or left. Now I know that aligns with what I've drawn, but go back to the first example. Could we have pulled it to the left and it moved to the left? So my dash box, it's going to move to the left. Maybe we pull it to the left. And so here would be left and left. What angle separates left and left? 0. So the force is left, D is left. And so the angle would be 0 degrees, and cosine 0 is +1. And so those top two, as long as you're pulling it in the direction it's moving, you have positive work done. It doesn't mean to the right, it doesn't mean up, it just means the direction of your force and distance agree. And wouldn't the most recent that I drew, wouldn't that one be speeding up as well? If you pull it to the left and it moves to the left. And so this is going to be speed up. Notice that's what they have in common, right? So it doesn't matter what direction you pull it, if it moves in the same direction that you're pulling it, is going to speed up. And you could draw the opposite picture of friction to the right, but it's moving to the left, right? Correct? And you still get 180, you'd still get negative, it'd still be a slowdown. And so we get a little summary here. And so for work, the sign does not mean direction. If you have a force and D in the same direction, two things you know. It means the object's going to speed up, and it means you have positive work being done. What if F and D are in opposite directions? What's going to be true? What's going to be true? If you pull something the opposite way it's moving, it's going to slow down, and it's considered to have what kind of work? Negative work. But the positive and negative do not mean direction of work. Work is scalar. You don't have rightward work, okay? So just be careful on that sign. It's weird. We do have a sign, it just doesn't mean direction, since work is a scalar quantity. So the cosine theta will tell you the positive and negative. Correct. The cosine theta is there. Right. Yeah, the cosine theta is there to kind of give you that positive negative relationship, or you just draw it out, look at the picture, you can tell. Okay. Now I will warn you, I can think of at least one example right now where you can have sine theta to calculate the work. So I don't want you to get caught up on cosine theta. Yes, it's correct as long as you know that angle is being defined as the angle between force and distance. So one more example, and then we'll get to the theorem, the work energy theorem. And so my last example, what if I put that box on a ramp? Ramps have angles, right? Typically with the horizontal plane. And so we've got this ramp angle. Well, if I just let it slide down, okay, let's go and draw a force diagram. Ooh, still drawing force diagrams. Quit quincing that face or whatever, right? Get over it. No, we're pros at it now, right? What forces are acting if I just allow this box to slide down? Is it frictional? Sure, let's make it a rough surface. And so let's go back and start with gravity. So gravity acts on this box, what direction? Straight down. Force is still a vector, arrows. Normal force, by definition, acts perpendicular to the surface. So here it would be up and to the left. Tilt your head, right? And so we got a normal force in the up and left. And then we said, okay, let's make it a rough surface. Friction force would act on it You had to remember what direction I said it was going. We allowed it to slide down the ramp. So you could put a velocity vector on the side to let you know what direction it's going. But that would mean friction is working to the up the ramp, right? And up, right? Or correct? So that frictional force. Now, those labels that I put on the force, each of these forces has the potential to do work. So let's go through this. Who's doing work? Is gravity doing work? Is normal force doing work? Is friction doing work? Okay, so let's go back to the start. Is gravity doing work on it? Ooh, what if I told you yes? No, I'm not. So let's go in here. What direction is the box moving? Down the ramp. So our D is going to be parallel to the surface. And remember that, there it is. When boxes or objects are on a ramp, what do we do special with gravity? Components. Remember, there's a perpendicular component. Let me rearrange some stuff here. Put my label on the left side. We have a parallel component of gravity. Well, is that parallel component due to gravity used or determined by cosine theta? No, because where's that ramp angle in that triangle? The angle is at the top here. Okay, so that's our ramp angle, but it's not the angle that separates F and D. So be careful here. FD cosine theta is not always the ramp angle. Okay, so for work done by gravity, I need the force of gravity that's parallel to our D. And so how do I find that parallel component of the gravitational force? mg sine theta, because it's opposite, right? It's opposite theta ramp. And so it would be mg sine theta, and that's a ramp angle. And isn't this force down the ramp? And isn't it moving down the ramp? So if you wanted to say cosine theta after all this, what theta would you put in? And so this is a separation angle, hence why I'm putting subscripts on my two different angles, right? By the way, at the end of the day, you don't have to do this, but you got to know those are different angles. One's a ramp angle, one's a separation angle. And so if both gravity are pulling it down the ramp and it's moving down the ramp, what is the separation angle? It'd be 0, and cosine 0 is what kind of one?
Positive.
Positive. Now, once we put numbers in, we may not get 1, but y'all, you have a positive work done by gravity. What's this object going to do if we allow it to slide down the ramp? It's going to speed up, right? Shouldn't positive work speed an object up? Isn't that what we said? Yeah. So gravity, if you just focus on gravity, it's going to try to speed the object up. Nitty gritty, right? Okay. What about normal force? Does normal force do any work? Well, normal force is going to be perpendicular, so Fn is kind of this way, and D is this way, parallel to the ramp. What would your angle be? Well, you could put cosine 90, which if you plug it in is going to turn out to be 0. And so Fn, work in would be 0. The force and the distance it's traveling, the normal force, are perpendicular to each other. And by definition, to do work, there has to be a parallel piece of the force. And there is none for normal. So it's just zero. End of story. Good deal? What about friction? Is there work done by friction? Yes. And so we can look at it as the work done by friction times the distance. Oh, I'm sorry, force of friction at that point. The work of friction equals the frictional force times distance. And then you can either just know, okay, parallel, or you can go for the equation cosine theta, and that's a separation distance angle. And so we have a frictional force that's up the ramp, a distance that's down the ramp. Both are parallel, so yes, it will do work. But what angle separates up the ramp and down the ramp? 180, so it would be an angle of 180 degrees. So what kind of work is friction gonna do? Negative work done by friction. Now, whether the object is speeding up or slowing down, what's friction trying to do? If you just look at friction, it's trying to slow the object down. So how do we know who wins? Does gravity win or does friction win here? Well, enter the work-energy theorem. So I'm going to use this to get us into the next piece. Questions so far? Let me pause. That was a lot. I know, I kind of got excited. Day one back, boom, boom, boom. You just thought you were still on break. No, no. Digest it, ask me questions. I promise you're not alone. All right, let's smush it all together. How do we know who wins? Does gravity win and it does speed up collectively? Or does friction win and this object's slowing down as it goes down the ramp? And so when you put it all together, well, what do we call it when you put forces together? Combination, AKA net force. Well, guess what? If I put all those works together, we're going to get a net work. So this is part of that theorem. Net forces tell us how the object is accelerating. And hopefully you remember acceleration tells us if it's speeding up or slowing down. Well, your net work is going to get into energy. And so it's equal to a delta KE, or you can also say delta EK, or you can say just delta big K. Now I put that one there, that's on the AP formula chart, just a capital K. Now again, no one consulted me, but I usually don't write it that way because I'm not always case sensitive when I write. Look at your formula chart, find big K and little k. Big K stands for kinetic energy. Little k stands for spring constant. That's coming next week. So within the same unit, you got to either pay attention to K sensitivity, or what me and a lot of other people do, we say KE or EK. Your IB friends are learning EK, but a lot of people on the digest, textbooks, KE. And so just know it's two letters to represent one thing. Don't think it's K times E. It's a collective combination variable, yes? Okay. And so this kinetic energy, what is kinetic energy? Y'all have learned this. It's the energy of movement, motion of a moving object. And so it's the energy of a moving object. True story. And no, we do not have energy of a not moving object. Okay? There's not an opposite. It's the energy of a moving object. So in other words, it has to have a velocity. It has to have a speed. Okay, so the object has to have speed. So right now, I'm not moving. Do I have kinetic energy? No, but how can I get some? Something's got to push me, right? And if I walk, ooh, quiz time. If I walk, who's pushing me? I can't push myself. The ground. I push on the ground. Newton's third law says the ground pushes back on me. So the ground, that frictional grip, is it all coming back to you now? The gripping friction is what's doing work on me. So friction doesn't always slow down. Remember, walking is that special case where it causes motion, right? Gripping, static friction. Okay, and so a change, delta. What does delta mean? Well, what's the mathematical delta mean? Don't go COVID on me. First year I've ever had to say that, right? Not sum, that would be sigma. So remember, this one is our sigma. That means sum of all the works is going to equal a delta, a change in kinetic energy, okay? Or how can what math can you do to find that delta KE? Delta anything is what math? Final minus initial. So we can keep it going and say the sum of the works equals KE final minus KE initial. And so maybe that box up above started from rest. So maybe it starts at rest. Oh, I guess I should give you the equation for kinetic energy, right? Kinetic energy on its own, so on the AP formula chart, and it should be there, K, or KE, is what you'll see me write, is equal to 1/2 mv squared. Now we're so used to dealing, I think all semester one, it was vector, 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 right? Everybody was a vector almost, not time, but a lot of our big characters of the fall semester were vectors. Well, now work is scalar, right? And if work equals some kind of energy, y'all, kinetic energy is scalar. Let's write that down somewhere. Kinetic energy is scalar. So does kinetic energy care if I'm moving right or left? No, that V is actually a speed in this equation. Actually just a speed. Even if you said, oh, I'm moving to the left at -2 meters per second. What are you going to do to that -2? You're going to square it. And what happens to a negative number squared? It goes away. So kinetic energy doesn't care if you're moving right or left, up or down. Throw a pin in the air, right? You can do that. Kinetic energy doesn't care. Kinetic energy, you either have it or you don't. And how do you have it? Well, somebody did work on you. Somebody, some force, right? Is this making sense? Oh, I haven't talked units. Let's talk about units. There's so much. Haven't I went beyond page 1? Sorry, paper people. Write small. Okay. The unit for kinetic energy, and I'm just going to say energy because next week when we learn about potential energy, it's going to have the same unit. So the unit for energy and the unit for work is what? I think I heard someone say it. You've learned it before. Capital J for joules, spelled maybe not like the family jewels, or not like the diamonds and rubies and sapphires, right? So joules, capital J, that's the unit. Now, if we go back and just look at what makes up a joule, well, if you remember, work was equal to a force times distance. What's the unit for force? A Newton. And what's the unit for distance? Meter. And so a Newton meter is equivalent to a joule. So technically both are correct. And so this is our equivalent unit. Now maybe on the free response portion of the formula of the AP exam, you know, you probably won't have numbers very much. You probably won't have to worry about units on that, but sometimes they do ask equivalent questions, typically in multiple choice. Which of the following is equivalent to a joule? A Newton meter, a Newton per meter, a Newton squared meter, or they'll, you know, make up some other kind of wrong combination. It's a Newton times a meter. That's equivalent to a joule. Okay, so now we know the unit. Now we know the connection with kinetic energy. Okay, so that speed up or slow down has to come from somebody doing work on the object. And so let's get back to our object sliding down a ramp. We said gravity is trying to speed it up, friction's trying to slow it down, and normal doesn't do any work. So we don't need to worry about it. And so we come down here and we make a net work statement. And you have to remind yourself work is scalar, so it's going to look a little different. So just a reminder right here at this moment, it's a scalar quantity. And so net work is equal to the work done by gravity and the work done by normal. Don't worry, I'll zero it out. Plus the work done by friction. And it's scalar, so I plus, plus, plus. And so then we can start saying, well, normal force was 0. So I had a positive work done by gravity plus 0. Plus a negative work done by friction. And so at the end of the day, the net work portion would be the work done by gravity minus the work done by friction. And that's going to equal the final kinetic energy minus, well, we said it started from rest, and so that would be minus 0. So we're playing the same games with our equation as we did in the fall, right? We have one big theorem that the net work on an object is going to change its kinetic energy. That's the theorem. Net work equals change in kinetic energy. It's kind of on the formula chart too. So go back to the formula chart. And it may not be written exactly that way, but I think somewhere in the halfway, it says change in energy equals work. Now that's generic. What we've done is say that net work equals a change in kinetic energy. That's because later on in 2 weeks, we'll have 2 more versions of that work energy theorem, okay? But this one is the one we're going to spend a week on. Good deal? And without numbers, there's no way to know who wins on this one. If it's going to speed up, so let's do that. We'll do our special cases. So if the box on the ramp speeds up, who does more work? Gravity would have to do more work. So WG would be greater than WF. The work done by gravity, it'd have to pull it more than friction is resisting. If the box on the ramp, just so we know which example we're making a callback to, if the box on the ramp slows down, and yes, that can happen, then what can we safely assume? Friction does more work. So friction is doing more work than gravity. Okay. I'll take another pause break, let that digest, ask me some questions. We introduce kinetic energy, what it is. It's scalar. Doesn't care what direction you're going, you got it or you don't. If you're moving, you have kinetic energy. Boom. Oh, by the way, what's the M there? Mass, you got to have mass too. Okay, mass matters in kinetic energy. And the 1/2 mv squared, it's actually a derived equation. I think it's probably in your book, or we can do that maybe next time. I'll save that for another day. You don't need to know how it's derived, but it is a derived equation. And then what else? Units, equivalent unit. And then the work energy theorem is net work equals a change in kinetic energy. Speeding up or slowing down means somebody's doing a different amount of work. Think we're ready for some examples? I can't think of what else to add to notes right there, other than just doing different examples, but we'll use practice problems for that. Oh no, I can think of one more. Let's do one more basic example, okay? We did one with some angles. What I haven't done is that vertical falling object. I talked about throw a pen up in the air, right? So let's do one last example of that. I'll just slide to the side. So another example. What if we throw an object with up, so I'm going to call up the positive direction, and notice I brought in that VI. I stands for initial, and so I'm going to throw it up in the air, neglecting air resistance, right? What's it going to do? Y'all know this. It's going to start slowing down, and so we can show that with our velocity vector getting smaller. And what's causing it to slow down?
Gravity.
Gravity. So don't forget there's a gravitational acceleration, AG, acceleration due to gravity, or just little g. And then it goes up, 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 up. What happens at the top of the peak? It comes to a split-second stop, so the velocity becomes 0. What about the acceleration? Oh, I heard both. And so that's the catch. So somewhere on the AP exam, you're going to be tested on this. When it comes to a split-second stop, acceleration, gravity doesn't quit. And so your acceleration is still in the downward direction. It does not equal 0 at the top. Good deal, remember that? If it stopped, the pen would never come back down. But eventually, since gravity does continue working on it, what's the other part of the picture? Right, so I'm going to slide over just so I don't clutter. But now on the way down, so this first picture is the up. Now we're on the way down. And so we're going to start at a 0 velocity, and it's going to speed up, right? It's symmetrical as long as I end at the same place. Y'all remember the symmetry? Projectiles? But now we're moving down. So remember, that's a negative velocity. The whole time, gravity's always pulling what direction? Down. So there's your review. Now let's take a look at it from forces and work. What's your force diagram look like on this object? Force diagram. And I should caveat when it's in free fall. So when in free fall, it's only FG. Up, down doesn't matter to force diagrams, right? They're not motion diagrams. That's different. And so the whole time, we've just got the force of gravity down. Does that mean that gravity has the same kind of work? Well, no. On the way up, the distance is up, but gravity as a force is pulling it down. And so the work done by gravity would be negative. Hello.
That's a deliberate for you? Is that right?
Yes.
Okay.
Maybe it was found in the basement over Christmas. 2-year-old ID. Okay, maybe you know the story behind that. I don't know. Okay, so on the way up, because it's slowing down and because gravity as a force has a 180-degree angle of separation with the up distance, it's doing negative work. But what about on the way down? It's moving down, gravity's pulling it down, and so it should be a positive work. Okay, and doesn't that align with the whole slowing down on the way up? And then speeding up on the way down? Okay, so not a bad example there. Just pointing out that one force never changes direction, but the kind of work it does change. It depends on the motion. Okay, let's move to page 2 finally and do some examples. So these are, page 2 going to be our basic example type. Getting a little more closer to AP towards the end of the packet, okay? And so we've got a van, a real heavy van, with a mass of 1,500 kg. Review time, do I need to convert that? Kg, do I need to convert it to just grams? No, remember kilograms is good, don't convert it. It's the only SI unit with a prefix, okay? And then we have a bike with 20 kilograms. So notice, very different mass. It says if the van and bike have the same kinetic energy, compare the force needed to stop them. Stop them, what do we know? It's going to slow down. There's got to be a negative work, okay, so a negative work to slow it down. But it also tells us final velocity or final speed would be 0. And it says over 10 meters of distance. Now, it's not really, final answer is a number. It's really a ranking. The numbers are there just to help us. And so, who's going to need more force to bring it to a stop, the van or the bike? And your gut instinct is van, but your gut instinct is wrong if you look at nitty-gritty details about the problem. It's this is what students call a trick question, but this is what teachers call, are you reading the question and looking at the details? The detail is same kinetic energy in the start. So they have the same initial kinetic energy. They both come to a stop, so they both have the same final. So same kinetic energy initial and the same final kinetic energy. So tell me what their change in kinetic energy is. It's the same. And using the work energy theorem, what does a change in kinetic energy equate to? Net work. And so they have the same net work. Well, they both come to a stop over the same 10 meters. And so they have the same distance. So if they have the same net work and the same distance, then they have to have the same net force to bring them to a stop. So final answer, same. And you're like, what? So what's the unknown here? What do we not know? That's kind of the truth to the story. We don't know the initial speeds. What if the van is going super duper slow and the bike is going super duper fast, right? So the van could be going very slow, like 1 mile an hour, okay? And the bike could be going maybe 15 or whatever miles an hour, a whole lot more, right? And so they have the same kinetic energy, but does that mean they start with the same speed? No. So it's not the same initial velocity. And I didn't really mention this on page 1, so let's do it now. Kinetic energy is that 1/2 mass times speed squared. Well, the van has a much bigger mass, if they have the same kinetic energy, what kind of speed does the van have to have? A very less speed. The bike has a very small mass, so it's going to be moving faster initially. We know they both come to a stop. So that's kind of the caveat. In your brain, you said it took more force to stop the van. Maybe you were saying in your mind they were traveling the same initial speed, but that wasn't told to us, right? So again, AP questions, read for detail, be careful, okay? Make sure your assumptions are safe assumptions, not generic assumptions. What do you mean? You can use either. Yeah, are you talking about the kinetic energy? Yeah, so just to kind of rehash the theorem previously, net work equals a change in kinetic energy. Well, that's a final kinetic energy minus an initial kinetic energy. And so the mass is not changing for any one object. And so it'd be 1/2 mass final speed squared minus 1/2 same mass times the initial speed squared. So you got your subscripts on the speeds, you got your subscripts on the kinetic energy. We see, other force subscripts on the work piece. Mass, as long as you're doing it for each object separately, that would be the same in this one equation. So the change in kinetic energy of the car, change in kinetic energy of the van. Good deal? Or I'm sorry, bike, not car. All right, look at example 2. Again, not really doing numbers here, just doing some concepts. It says rank each force according to the work done by that force. And the picture shows a particular box. It says it's going to have a distance d, and we'll assume it's moving to the right. So give yourself a little velocity vector. Okay. And the arrows are all the same force, but notice what's different about them. The angle. So that's the only thing different. I've got 5 same forces at 5 different angles. Notice that 1 and 2, well, this is like our pulling above the horizontal, right? 3, you're pulling straight parallel to the surface. And 4 and 5, it's like our shopping cart example, right? They're getting pulled into the ground, below the horizontal. That doesn't mean the cart's going underground. It's just the direction of the force, right? And so assume the same angle up from the horizontal as below. And what that's saying is the angle of 2 is equal to the angle of 4 if you kind of use 3 as the horizontal axis, right? As your reference. Who's doing more work? Why is 3 doing more work? Okay, and so the work done by 3, notice we're still using subscripts for identification purposes, right? So they're all an applied force. We're ignoring gravity, normal, and any friction here. It's just based on these forces. And so the work done by 3 is equal to the force done by 3 times the distance, and then either conceptually considering the parallel piece or throwing in cosine theta. What's theta for example 3? It'd be that 0 degrees. And so we're going to get a positive work, no components needed. Everything is in that horizontal direction. And so, yeah, it's going to be the greatest, and I'm going to write that it's a maximum work here. Well, what about 2? Let's look at 2. It'd be the force of 2, which, by the way, the forces are the same. D is the same, but what's different? Cosine theta, now I'm going to make a number up here just to kind of prove the point. What if we say that 2 is, 30 degrees above the horizontal? So I'm going to say cosine 30. Is it still going to be positive work? Well, that component of the force is rightish. It's moving to the right. So we're still going to get a positive work, but a smaller, right? Or correct? Now I got to change my verbiage. And so it's not a max, but it's going to be less than the max. And what about 1? Well, again, F1 and D are going to be the same. The only difference is maybe now it's at a cosine 45. Well, cosine 45, compare that to cosine 30. Is this going to be between max and less? Cosine 30, cosine 45. Somebody grab a calculator. How is our 45 going to rank with the 30? Give me the numbers. What's cosine 30? 0.86. Okay. 707, you said? Okay. And so as angle goes up, what happens to the component? It gets smaller, and hopefully that makes sense, right? The force is becoming more vertical. And so it's going to be still a positive work. We still have a right word, but now instead of max and less, maybe I say least. Where does 4 and 5 fall? Now it's 30 degrees below, but isn't it still to the right? Isn't it still 30? And so work done by 4 would be equal to the work done by 2. And where does 5 fall? Equal to the 1. And so final ranking, what would we say? 3? There we go. Everybody good on that? Now the up-down difference. So what does change? So hopefully you remember the difference of pulling on the shopping cart and pushing on the shopping cart. When you push down into the shopping cart or the object, we're pushing it more into the ground. So what other force is actually increasing when you push down on an object? Normal force is increasing. Is normal force going to do any work if it slides to the right? Normal force is vertical. No. And so the force is increasing, but the work done by normal is not going to be anything. So just note to self that, for 4 and 5, the normal force increases, but work done by the normal force would be 0 because the force is up, but the distance is right, and that's a cosine 90, which is 0. Nothing parallel about perpendicular. Okay. Similar, but now we actually have one type of force here. It says we got an object that's going to start from rest. And how do I know that? Initial velocity is 0. And then we're going to pull up and to the right with a force. You can call it an applied force at some angle at the horizontal. It's going to move some distance, d, and have a final velocity of something. And they tell us it's a rough surface, mu k, right? So we know there's friction. If instead your force was applied at an angle below the horizontal, would VF be bigger, same, or smaller? So kind of an extension of the one above, right? instead of changing the force at 5 different angles, we're just starting above and below. So look at 2 versus 4. Is VF going to be the same, or will it be bigger and smaller? Well, what did we say? When you push down on the object and push below, so your new picture would be so F would now be below, angle remains the same, force remains the same. The only difference is above versus below. Your horizontal piece is going to be the same, right? So the horizontal component would be the same, but your vertical component is where it changes things. What did we say increases when you push down on an object? Normal force increases with an angle below. Well, is the answer so what? Same speed? Well, if normal force increases, think about it. That means it's pushing into the ground more and more and more. What else is going to increase because of the normal force increasing? Friction, remember, is equal to mu K times Fn. Well, remember, mu K is dependent on the surface. So if the surface doesn't change, it's going to be the same. But if our normal force is increasing, that means there's more friction. So we have more frictional force, meaning the work done by friction is going to increase. Notice I'm taking it to the work terms. Technically, you could answer this without work and energy. But if the work done by friction is increasing, but the work done by the applied is the same, then what's going to happen to your kinetic energy? More friction means you have a smaller, you have a smaller change in kinetic. Because again, that net work on the object would equal a change in kinetic energy. Net work here, who's doing work? Let's do that. Who's doing work on this object? Either. You get the same answer. Who's doing work? The applied. And is the applied doing a positive work or negative work? Okay, so we got a positive work applied. What about normal? No. What about gravity? No. Why not? Those are vertical forces, but it's moving horizontal. And so that's going to be 90, right? What about friction? Yes, as it moves to the right, friction is going to be less, so it's plus a negative. And so if work done by the applied is the same, but friction is increasing as we push below, then what's going to happen to the change in kinetic? It'd come out smaller, right? Okay, so what does that mean about the speed? If you have a smaller change in kinetic, and it all started from rest, so KEI would be 0. So really, we're just looking at final kinetic energy. And so final answer would be A. Is your final velocity going to be bigger, smaller, or same? No, from whenever you pull up on it to when you push down on it. That's what we're comparing. Smaller. Okay. A smaller final kinetic energy when you push down means you have a smaller VF. Okay. How do we feel? Fantastic. Page 3. Can y'all do some numbers? Now, I know I haven't done numbers, but I've done enough to get it set up. How about y'all try number 4, okay? That might take a little longer because you've got WA, WF, and we want numbers there, mu K. And then they say, what would the final velocity be if the 45 degrees given above the horizontal was now below? Sound familiar? Okay, except now they want numbers. And so give all these numbers. Hint, hint, step one. What's a good idea to start with? Force diagram, free body diagram, whatever you want to call it. Draw it out. And you'll need a calculator, so go grab one. They've been charging since yesterday. Okay. I'll give you about 10-ish minutes, 12 maybe, and then we'll kind of quickly go through it. Okay, so let's walk through this. I have my diagram. Now, one thing that you weren't really told is what direction is it moving? So I just kept it nice, right? It moves forward. I'm going to say it's right, just kind of keeping it nice to myself. So I assumed it's moving to the right. And then it tells us that it's being pushed with an angle above, or maybe it's pulled, push, pull, who cares? But FA is going to be above the horizontal. And so my diagram shows FA at an angle. It has FN. Notice it's smaller than the weight. Why? Here's something we haven't talked about today. Why is FN less than the weight? Because there's an applied force in the upward direction. So together they balance the weight, right? But FN should be smaller. We're helping it. And if I'm pulling to the right, friction on this would act to the left. So there's my diagram. And then I identified who's doing work and who's not, okay? That's usually, you don't draw a work diagram, but you take the forces that are in your diagram and say, okay, who's doing work? Well, why is normal and gravity not doing any work? They're in the vertical, but it's moving in the horizontal. And so conceptually, those are not parallel. They are perpendicular forces to parallel motion, 0, 0, normal gravity. Applied, I made positive. When you pull on something or push something, you're trying to speed it up, right? And so I pull to the rightish, it's moving to the right, so positive applied work. And then if I'm pulling to the right and friction's pulling to the left, but it's moving to the right, that would be a negative work, right? So I'm not using cosine theta for that. I'm using the concepts of knowing opposite direction, speeding up, slowing down, back to those page 1 concepts. Okay, they also tell us the distance, 15 meters. Again, I assumed it was moving to the right, so I had to draw that out. And then 7 meters per second is given as the final velocity. What number can we all make up as initial? We can assume it starts from rest. So I said initial velocity would be 0. Now I'm going to zoom in. There's actually 2 different ways to approach part A. To find the work done by your applied force, you got to stick with the applied work. You need applied force times the distance. And so you can say FAD times cosine theta, or notice what I did in that second part. I already know work is going to do positive, right? Work. And so if I know it's moving to the right, I need the rightward parallel component of that applied force. That's not in my diagram, but I can add it. Isn't FAX the parallel component that's parallel to the motion? And so notice the cosine theta. Where's theta? They said it was with the horizontal. Notice cosine 45 can go either place. It can be FD cosine theta or F cosine theta times D. So it's the same math, but just a different approach. Yes? And you should get the same thing. So 200 times 15 times cosine theta gets us what answer for WA? 2121? Okay. Now, walking around, I saw some different numbers. And so let's all try it again. Oh, one thing I haven't said today, but we said it a lot in the fall, calculators must be in degree mode. And so let's make sure we're in degree mode. Sorry. So 200 times 15 times cosine, they said it's 45? Yes. And I get 21. So if you didn't get 21, see if you can find your error so you don't make it again, right? Everyone good on that one? Explanation and math. And notice I put a J. J stands for joules. So that's your final answer to part A. Part B got some of you stuck, okay? It wasn't, I don't want to say it was intentional, but it's typical at this point. So for W friction, you might say, well, to find the friction, I need the force of friction times D cosine theta. Oh, force of friction is mu Fn, but wait, what did they not tell me? But I'm going to solve for in part C. Mu. So I can't do this approach in part B. So I need another way. What is plan B? Well, remember, to speed up or slow down, there has to be a change in kinetic. And what equates to a change in kinetic energy? It happens because of a net work. Well, who's doing work on this object? Applied, we said, is doing work, right? We just found it. And then there's also the work done by friction. We said, we don't know what it is, but we know it's going to be negative. Now, a couple different approaches. Do I put the negative in now, or do I get a negative answer? Tomato at the end of the day. I'm just going to leave it and solve for it, and it should come out negative. But that doesn't mean left. I know that in my diagram, friction is left as a force, but it doesn't mean left work done by friction, okay? The negative is there because the force of friction and the distance it's moving, the direction of motion, are 180 degrees opposite, okay? It's trying to slow it down. That's why friction work due to friction is negative. And so this is going to be the route we take. And so let's take that change in KE one step further. And so change in KE is that final kinetic energy minus initial. Kinetic energy is that new equation, 1/2 mass times final velocity squared minus 1/2 mass times initial velocity. Wait a second. What do we say about initial velocity or speed? It's 0. So if you have 0 initial speed, what's your initial kinetic energy? 0. So it zeros here, that whole thing zeros. And so we can kind of, use this step to get our final equation. And so WA plus WF equals that final kinetic energy. How do I solve for WF? I got to subtract the work done by the applied force from both sides, which we found in part A. And so we should be able to plug our numbers in. They said the mass is what? 50. And the final velocity or speed was 7. Don't forget to square it. Minus that 21. And so be careful as you plug this in. You only want to square the 7. Or 7 squared is 49, and half of 50, 25. So what's 25 times 49? Plug it in. Let me know what you get. 25 times 49. Wait, 4,000? Okay. 1,225 minus 2,2121, right? So it's 1,000 number minus a 2,000 number. We're going to get a negative answer. And so the work of friction is going to be a negative. Tell me what you get. And the SI unit for work, joules, same as energy. And so did we get a negative? Yes. Does it mean left? No. It means it's slowing it down, right? Okay, how would you find mu? Well, hey, that mu FN that didn't work before, now you can use it. And then D, so we'll quickly start here next time. Really, I can't think of new notes next time. I think it's just practice for the next couple days. Okay, I think so. And then we'll have our quiz next week. Yes, hold on. All right, pack up and y'all head out.